In our last video, we discussed the elements that make up an IAM security policy. In this video, we'll see how these policy elements work in practice by controlling access to an S3 bucket in accordance with our company's high-level security requirements. Let's start with a common deployment scenario and policy requirements. Suppose we have a simple application deployed entirely in AWS. And let's suppose the application does the following. It deploys to AWS using an automated delivery pipeline. It runs on AWS Lambda using the app IAM role. It's supported by a customer service team, and it stores data in the sensitive app data bucket. The deployment must also implement the organization's high-level security policy requirements. The first of which is to attain least privilege. This means allowing only explicitly specified principals the actions and access to data they need to perform their business function, and denying access to all other principals. The second requirement will be to maintain encryption at rest and in transport. Many people approach this by creating an identity policy for the application's IAM role, so let's start there. We can create an identity policy for the app role that grants read and write access to the sensitive app data bucket. Once attached to the app role, this identity policy will allow the application to read and write data in the sensitive app data bucket. But problems are lurking. This identity policy grants access to the app role in a minimal way, but it doesn't achieve the full mission of protecting the sensitive application data. For example, what if the app role has another identity policy attached that allows it to delete objects in any bucket? Or what if other IAM users and roles have the ability to read objects from any S3 bucket in the account? These scenarios are very common. Many identity policies include statements that don't limit the resources they apply to with wildcards either. This is the case when using AWS managed policies like read-only access or administrator access. AWS managed policies always use resource wildcard star since they must be usable in any customer's account. Depending on the use case, wildcards are useful, necessary, and dangerous. You'll want to carefully analyze the scope of resources the wildcard matches now and what it could match in the future as resources change. Then decide if the match scope is appropriate. We've just seen that we can allow access to sensitive data with an identity policy, but we can't deny unintended resource access with identity policies in a scalable and maintainable way. It's impractical for engineers to continually be aware of and evaluate every policy for every identity in an account. It's really impractical to update identity policies every time a new resource needs to be protected. So how will we implement the least privilege and encryption requirements for our sensitive data? We need to block unauthorized and insecure access to sensitive data with a different approach, resource policies. To actually implement least privilege, we need to turn the problem around. We need to deny unauthorized and insecure access to the sensitive data using a resource policy attached to the bucket. This flowchart here shows how AWS IAM evaluates policies. Any allow in the policy evaluation chain provides access to the resource unless there is an explicit deny. And notice that both identity and resource policies may allow an action. Effects are calculated with this precedence. Explicit deny by matching statement overriding allow, explicit allow by matching statement, or implicit deny when no statement matches. Resource policies apply security rules directly to a resource like an S3 bucket or KMS key. In practice, there are relatively few sensitive data resources in an account, so a more practical approach to protecting the sensitive data is to attach a resource policy that enforces least privilege and best practice. Begin creating your resource policy by identifying precisely who needs access to the bucket and what kind of access they need. Suppose interviews with the application delivery and customer support team reveal the following access requirements for IAM principals. CI user needs administration capabilities to deploy application updates. Admin role needs administration capabilities to fix urgent problems. App role needs read and write data capabilities for the application to function. And customer service role needs to read data capabilities to investigate problems. All of these identities and application resources exist within a single AWS account, 111. Now we have enough information to provision the intended access in the steps that follow. We'll start by creating a policy with a deny everyone else statement that blocks access from all principals who do not need access to the bucket. The deny everyone else statement jumps right into the deep end of the IAM policy concepts. This statement denies all IAM principals in account 111 the ability to invoke any S3 API actions on this bucket whenever the condition is met. That condition is met when the requester's IAM principal ARN is not one of the intended principals, admin, app, CI, or customer service. This statement narrows the scope of who can access the bucket to these four principles, no matter what their identity policies allow. Remember, explicit deny takes precedence over explicit allow in AWS IAM. We also want to enforce the organization's encryption policy. Require encryption in transport with a deny insecure communications statement. This denies all principals the ability to invoke an S3 API action using an insecure transport. This forces clients to use HTTPS. The AWS API will deny any request made with HTTP when it reaches the AWS API endpoint. And just a note, if requiring secure transport causes a problem, consult the relevant AWS SDK docs and reconfigure the application to use the HTTPS transport scheme. Next, let's enforce encryption at rest with these deny unencrypted storage and deny storage without KMS encryption statements. These statements force clients to do two things. First, all S3 put object operations must use AWS's server-side encryption services on every put. Second, the encryption must use an encryption key managed by the AWS Key Management Service, KMS. Now, let's explicitly grant the access each of the principals need with an appropriate statement. Organize the allow statements by needed access capability, not principal. Organizing by access capability simplifies understanding what API actions principals may and may not perform on the resource. You will always know where to look to see if, for example, a principal is allowed to write data. Grant an access capability with a statement using this form. The SID describes that the statement allows a particular capability, such as reading data or administering resources. The resource element applies to all objects in the bucket and the bucket itself. Buckets and bucket objects are distinct resource types. This is an important detail. Access to a bucket is identified and evaluated separately from the objects inside it. Most AWS API actions apply to a single resource type, though some API actions interact with multiple. The principal matches all AWS IAM principals in the AWS principal ARN array. A common policy mistake is to mismatch the API action and covered resource type. Allowing S3 put object to ARN AWS S3 sensitive app data is an example of this mistake. AWS may save the policy depending on what else is in it, but when you actually invoke S3 put object, the operation will fail. The action allowed puts to ARN AWS S3 sensitive app data, a bucket type, but S3 put object operates against objects. Now let's allow writes. The correct allow statement looks like this, which allows writes into the bucket. This statement allows the app role to put objects and also abort object uploads that are in progress. Allow restricted write data's resource element was narrowed to cover only objects in the bucket because the API actions pertain only to objects. The AWS API docs document which resource types each action works with. Now, allow the CI and admin principals to administer the bucket and its resources with a statement like this one. Notice the long list of actions includes some that operate on buckets, bucket objects, and some where it's not particularly clear what type of resource applies. We can create similar statements to allow reading configuration as well as reading or deleting data. The full policy for this example appears in the appendix of Effective IAM for AWS, which is found at effectiveim.com. To adopt this least privilege model for your own bucket, replace the principals and bucket name with your own, then put the policy into effect by populating the policy contents into the bucket's policy attribute in CloudFormation or Terraform, the AWS CLI, or console. These all invoke S3 put bucket policy. Finally, verified principals can still access data as expected. Resource policies are stored within the scope of the resource and cannot be shared between resources directly. Now let's wrap up our example. This example demonstrated a few things. First, that the AWS IAM security policy language is flexible and powerful enough to implement fine-grained access controls to AWS API actions and data. Also, the AWS identity and resource policies created in this video implement our high-level security goals. However, it wasn't easy or straightforward to implement the policies we needed. The policy language is complex and effects are sometimes difficult to anticipate. We had to close off unexpected access from other principals with excess privileges in the account. Enforcing basic encryption requirements is possible, but took 3 separate statements. And the final policies constitute hundreds of lines instead of a few tens of lines you'll find in most getting started blog posts and examples. But keep in mind that the access control capabilities provided by the AWS IAM security service and equivalent in other hyperscale clouds have no common analog to on-premises data centers. AWS IAM is over 10 years old, but it's still very early, especially when it comes to abstractions that help teams go fast safely. Thanks for watching today's video. If you want access to all of the code that you saw here today, or if you want to learn more about how to solve problems in AWS IAM, please feel free to visit effectiveiam.com today and get your copy of Effective IAM for AWS. Thanks.